Hey everyone, thank you so much for joining us today. So, hope you all had a nice break and were able to get some dinner or anything else that you needed. We are going to be starting in just a minute with Tracy Weyand, and she's going to be giving the talk. She's from the Rose-Hulman Institute of Technology, and she's going to be giving a talk, Engaging Engineers by Design. So I will pass the floor to her, and I hope that y'all enjoyed this talk. Thank you for being here.
Yeah, thank you very much for coming tonight. I know it's late tonight, but since I was teaching all day, this was our only option. So this presentation is coming from a combination of projects that I've been working on, some with engineering faculty and others with the Semio community. Before some of my comments are going to make sense, I first want to introduce you to my school, to Rose-Hulman. We only offer science and engineering majors. So from that standpoint, my classroom is unique in that I know what classes are going to be taking in the future. And I know I'm very familiar with lots of applications that they're going to be using this material in later on. We're also on the quarter system, which is probably why our schedule looks a bit unusual and our order of topics is not traditional. Students here usually take 2 quarters of differential equations rather than 1. I'll talk a little more about that in a moment. One benefit that we have is that all students have the same laptop. When they are a freshman, it is issued to them. And all of those laptops have licenses for Maple and MATLAB along with other products. So I know what tools they have available to them, and I can offer them guidance and assistance in using those along the way, working through projects. Every single one of our students to graduate must take matrix algebra and differential equations 1. In that class, we cover first order differential equations, second order assuming constant coefficient, homogeneous and non-homogeneous. Related to that, looking at the characteristic equations, we get into complex numbers, particularly Euler's form, and finding complex roots to polynomials. Then we move on to the matrix algebra component, looking at systems of linear equations, then solving systems of linear equations, Gauss elimination, rank, number of solutions, all of that fun stuff. And the class ends with an introduction to eigenvalues and eigenvectors. Then the majority of our students move on to the second part of that course. That begins with Laplace transforms. And then we move on to systems of differential equations for the bulk of that class. And at the end, we introduce them to Fourier series. Being a relatively small engineering school, I am very close to lots of the engineering faculty, and they are continually coming to me going, didn't you ever show them how to do blah? And my answer is always the same. I always roll my eyes, nod my head, and go, of course we did. But whether they remembered it and whether they are figuring out how to use it in your class seems to be a completely different story. They really seem to struggle making that connection to what they've seen in their math class and then later what they need in their engineering class. This comment has come up so often that I've started asking myself, is this my fault? And thinking more about what I do and thinking more about how they're going to be using this in their engineering classes. And the conclusion that I came to is partially. Certainly it isn't all on me. If they immediately forgot how to integrate after Calc 2, that part is not my fault. But there certainly are things that both the mathematics department and some of the other departments could do to help cross this bridge and fill this gap. In particular, I've been working with a project recently along with physics faculty and electrical engineering faculty, trying to relate these concepts exactly, figuring out what mathematics they need for their classes and when they see that in our math classes. And here are a few of the things that have come up and I've noticed. First of all, inconsistent notation and language. The electrical engineering faculty member on the first day of class came to our meeting and was extremely upset that when she showed this graph to her students, every single one of them said, yes, this is a continuous function. The other engineering faculty and physics faculty were horrified at that, but the math faculty just laughed. And we went, of course it's continuous. They didn't have to pick up their pencil. Of course, we then corrected her and informed her, well, this isn't actually a function at all, so your question doesn't make sense. But in real world applications, this is what they're going to be seeing. If you're reading, for example, the voltage output on one of the meters, this is what the graph looks like with that vertical line in it. So students do have to somehow fill that gap and know what that vertical line really means is happening there. We've also found a lot of issues with assumptions on prerequisites. They believed that we covered complex numbers in calculus too, and that isn't the case. They don't see complex numbers, in particular Euler's form, until DE1, 2 quarters later. So having incorrect assumptions on what the students know at that current point in time, we found has also been an issue. And then finally, we have different solution forms for things is another thing that we found. And when we're doing second order equations in our DE1 class, I teach them it's some constant times cosine plus a different constant times sine if you get a complex number from the characteristic equation. But in electrical engineering, they use the sine with a phase shift form for that solution. And yes, they are equivalent, but that's one that students haven't seen yet, so need to be shown is equivalent at some point, whether that's in our class or their class. They, in electrical engineering, also use phasor form for complex numbers, which is another thing that even though they know a lot about complex numbers, by the time they're in our DE1 class, they've never seen it in that form before. So that could be jarring to them. So how can I design a class that encourages my students to be future engineers, where they will be doing plenty of design in their work? Well, the first thing that I do is introduce modeling extremely early in my classes. The first week is a general introduction to differential equations, and the rest of that week, so for us, that's 4 whole days of class, is introduction to modeling and just practicing writing down models given a description of the event in words. I then use the modeling first approach for the rest of the quarter, introducing them to a new situation or a slight adaptation of a situation we've already looked at, and then go, oh, look, and we don't know how to solve this one yet. So guess what? Today's the day we need to learn a new technique. It gets to the point by about halfway through the course that becomes a joke, and the students are laughingly mimicking me, saying, oh, yay, we need to learn something new. I have them work in groups on projects throughout the quarter, 2 or 3, depending on the exact class and how that course dynamic is working along with our course calendar for that term. On every homework assignment, I aim for 1 conceptual question. That could be something like, well, what do you expect this parameter value to be, positive or negative, and explain why? Or what do you expect the solution to do when this parameter value increases? Explain why. And I also make sure that there's at least 1 modeling scenario on each of those homework assignments as well. And there's typically homework each week. Finally, I include models on in-class assessments as well, since I've had lots of comments of, well, we see it and then never see it again, in their opinion. So I'll also show you in a moment how I do that. That first week, here's what a typical one of my worksheets looks like. I first give them a description of a physical situation and then go through and ask them these 6 questions, leaving plenty of room for them to fill in the blanks in between. The first one we do together, and then after that, I have them work in groups and pairs to figure out what they think the answers to these 6 questions are, how they can set up the problem and the solution technique before they actually know how to solve it. So, for example, the first one that we go through together is a typical Newton's cooling law example. And the expected answers that I would write down are the following. I'm extremely specific at this point in the quarter. I would say that T of T is the temperature of the cake in degrees Fahrenheit, T minutes after being removed from the oven. So in that statement, I'm defining my functions, I'm defining my variables, and I'm giving units to them so they can use then unit manipulation to help them set up a DE that makes sense later on. What we know, this line they're normally pretty good at. Once they have that notation, they're usually good at writing down what they were given. The thing that they actually tend to struggle with is number 3, writing down what they actually need to do and what they actually need to solve is why I've added this one to my list of questions over the years, because I found lots of students could set up a problem and then perhaps later in the quarter even solve the DE, but struggled to answer the exact question that the physical situation was asking for. So in this case, we're not just looking for the temperature of the cake. We're saying find the time F at which the temperature at that time is equal to 80 degrees. I get them used to considering any assumptions they might have made. And we talk later on in the quarter about how the models could, simple models they started with at the beginning, could possibly be improved to account for some of these assumptions. Finally, they get to the point of writing down an initial value problem, and I ask them to go through that and check every single term for units, right? Make sure you're not adding up degrees in this case to something that has degrees per minute, for example. And then as a last step, I ask them to do a sanity check. Okay, roughly, what do you think the answer is? Well, it shouldn't be 2 minutes, but it shouldn't be 2 years either, is a good guess. I ask them to look through at their parameters. Do you think this should be negative? Do you think this should be positive? And explain why. We go through what we expect to happen before they know how to do any of the mathematics. I really like doing that because I have found if I wait to do this until they do know the mathematics, then at that point, they'll start skipping it. If they don't get into this habit immediately at the beginning of the quarter, they will not do it later on. And that's when things spontaneously freeze, sitting on a counter, waiting to cool. I get asked the question a lot, how do I put modeling on an in-class assessment, a short 50-minute in-class assessment? Here are some example questions that come straight from my exams. Obviously, I don't have the physical situation here. You can adapt that. But then given a physical situation, these are the types of questions that I ask. You notice that I do not ask them to actually solve the model or answer one of those questions that looks like the one on the previous page. I have them do that a lot on homework. They clearly do that in the group projects, but I've learned not to do that on the assessments because if something in the model goes wrong, then grading the work after that of them trying to solve the model is horrible, and not only horrible, but at times unfair, because every once in a while, a student will write down a model in a DE form that they still don't know how to solve yet at that point in the course, and therefore they couldn't have earned the credit for that question on the solving the DE component. So I've learned to decouple those on my in-class assessments. The second thing that I want to consider in that design process of designing a class for engineers is, again, preparing them to be engineers, preparing them to be part of the decision-making process. All of our students that are engineering majors are required to take junior and senior design. And for the most part, they're not big fans of that class. And the reason is because it's the first time that they are dealing with real engineering situations, and that things aren't cookie cutter from a textbook anymore. They want to know what the answer is. They're used to there being a right answer. For the first time in their life, there's not necessarily a right answer, and they just have to make the best possible call and learn how to justify that decision. Engineering design classes are open-ended. As I was just mentioning, there's no one correct answer. So they need to get used to making decisions based on the information given. And I give them that opportunity as part of their group projects. So here are a few examples of some of the group projects that I have assigned over the years. One of them was a decoupled salt tank model, but there were multiple salt tanks, not just two. I believe there was 5 off the top of my head. Each of those tanks was representing a lake in a city, and all these lakes were connected by streams. And the question was, where should the city council vote to put 2 new water filters? I love this question because it's very easy for me to change the context of this question from one quarter to the next. One time I said that you want, for example, all water in the city to be as clean as possible, so it can be then processed and used for water in the homes. But a different year, I said, well, they want to make 2 of the lakes as clean as possible because they want those lakes to be able to be used for water sport activities. So they really didn't care if the other lakes are a bit more polluted. They want to get 2 lakes as clean as possible. And no, you don't just necessarily pick the cleanest 2 lakes to put the filter in and make it even more clean. It depends how the filter works. That's true if the filter removes so many grams of pollutants per hour, but that's not true if the filter removes a certain percent of contaminants each hour. I've had lots of creative answers to this problem as well, because some creative groups have got the idea of putting the filters in the connecting rivers rather than in one of the lakes, which is something I had never thought of before looking at these problems. Another group project I've given is asking for a proper course of treatment that a doctor should recommend for a patient. Various situations, but essentially the idea being there is some kind of contaminant in the body that can damage one particular organ. So you want to make sure there's not too much of that material at any point in time in that one particular organ. Is the best way to do that to have the blood circulation in the body slow down, so not as much of the contaminant gets there? Is the better way to actually speed up how fast the blood is moving through the body, but also have the liver improve how quickly it's getting rid of that contaminant? There's lots of possible variations on this one as well. The one I'm going to focus on for the rest of my time tonight is looking at a building model during an earthquake. This is related to, can be related to, in my phrasing, a spring mass system, which is something that we study in class. And it has students try to figure out what design factors should go into that building to make sure that with a minor earthquake, the building will not have any damage. So for a very simple first starter, we consider just a single story building, so we don't have to worry about how the different floors are interacting with one another, and looking at the entire mass to be a single point mass in the center of the roof. And we're going to be interested in how far the center of that roof moves. The idea being if the center of the roof moves too far, that probably means like in photo B, the entire building is moving a bit too far and we could start to have structural damage, if not complete failure. A very simple model for this, again, looks just like a mass spring model, where here K depends on inertia and elasticity of the building along with the height. So in their groups, I have them start looking at this project by answering the first 3 questions. Depending on how the quarter is going, sometimes I give them half minutes in class to do this. Other times I have them work with their group outside of class and email me their answers. But here are some first basic things to get students thinking about before they even start tackling the mathematics, just to try to get some intuition behind what's going on. For example, what do you think is going to happen to that movement of the building if the height is increased and there's a slight vibration? What do you think is going to happen to the movement of the building if there's a slight vibration and the mass is larger? And what do you think is going to happen to the energy when the roof is moving? The last 2 questions are really interesting because the answer actually is that it depends. The last 2 questions, the answer is it depends on if we are considering damping in our model or not. So again, I normally give them 20 minutes in class to talk about these and think about them physically with their teammates. I then challenge them within that same week to spend some time outside of class with their teammates and try to prove their conclusions rigorously, mathematically. And that's normally when they start picking up on the things like, oh, wait, it matters what gamma is. Depending on what gamma is, my answer might actually change. My main goal of this project is to focus on resonance, because that's one of our required topics in this class. And that is one of the required topics that they typically really seem to struggle with. I think that's for a couple of reasons. Now, having taught this class, I've lost track how many times. I think I'm on time 9 right now. One reason I think it's challenging is because they're used to thinking in terms of x of t. They're used to thinking in terms of maximizing their function rather than maximizing the amplitude or displacement. It is not intuitive to a lot of them that the displacement depends on frequency. They can immediately tell me, oh yeah, the stronger the earthquake, right? The larger the oscillation, the larger the forcing function, of course, the building is going to move farther. They does not dawn on them in the least. It's hard to convince them that the frequency matters too. So one of the aspects of this project I have them go through is do exactly that. Look at this model for a very specific set of numbers and a very specific set of frequencies, and notice in each of those, calculate the amplitude, see that they are different, make a picture that does look something like this. And then finally, another thing they really struggle with going through the idea of resonance and trying to find a resonant frequency is they're uncomfortable treating frequency as the variable. T is always the variable, right? Or X. They're not used to omega being the thing that they are trying to that they are taking a derivative with respect to in order to maximize the function. So with an oscillating force, I also have them explain why this is a reasonable oscillating force for an earthquake, at least for a small period of time. They analyze this for various values of omega, as I mentioned, and here are the 2 main questions that the project leads them to. Is there an earthquake that is going to be a problem? So I give them a particular value of A, I give them a particular magnitude of the earthquake, and I tell them the building cannot safely move more than this many meters without having some structural damage. So given that information, are any values of omega, are any of the frequencies going to cause a problem? And then the second thing I ask them is the opposite, giving them both the amplitude and omega, giving them what the earthquake is. How much damping should the engineers be designing into that building in order to keep it from moving too far, in order to keep there from being any structural damage? I got this last project from an engineering book by Koprika. Sorry, it's duplicated on there. I just realized that. But this last modeling scenario that I talked about is in the Semiode repository. Earthquake modeling part 1 and part 2. Part 1 without damping, if that's as far as you get in one of your courses, and then part 2 including damping. So that is all I have for tonight. I'm happy to answer any questions, but thank you so much to everyone for coming.
Thank you so much, Tracy. I really enjoyed your talk, and thank you for everyone who's here right now. Just as a heads up, the next talks will be starting in about 5 minutes. So if you have questions, feel free to stick around. But for those of you who would like to go to a different room at this time, feel free to do so. Thank you again for your time, and give it up again for Tracy for a wonderful talk.
Thank you. How many projects? So we are on a quarter system. They only have 10 weeks. I have sometimes done 3, but that is really pushing it because that only gives them essentially 3 weeks to work on each project and gives me no time at the beginning to get to know my students, to figure out good group dynamics ahead of time. So I have managed 3 in a quarter, but I think I'm going to stick with 2 from now on. If I had a semester, I would definitely do 3. I do change the projects slightly from term to term. I have about, for the one class, for DE1, I have 5 projects. So giving them 2 or 3, I have a little bit of rotation. I also have about 5 versions of each one of those projects, as I was mentioning, by just changing how the water filter works, by changing what the city council hopes to accomplish. I can quickly take a project from a previous quarter and just do some of those minor edits to it. That's what I usually do. So they have problem solving skills coming in, I will admit that, but mathematical modeling is extremely new to my students, is why I spend so much of my first week stressing and working on that. Yes, even in our calculus classes, they are given, say, small application problems. So problem solving itself is not new, but the mathematical modeling idea is. That's the part that I spend time focusing on the first week. If I'm understanding the question correctly, yes, that first week, I do start off with the definition of a DE, the definition of an initial value problem. So they know definitions, they just don't know how to solve anything yet when they're first starting to see these models. I will go ahead and give the floor over to Glenn at this point. Thank you.
Thank you again, Tracy.